remember we talked about that yesterday, that for some people, one is better than the other one. Personally, I like to remember the power rule has a -1 issue. And so I like this way better, but yeah, that way's fine. So it's the integral of u to the -1 or 1 over u. Right, natural log. Now I don't even know how to write it. And of course, then we have to substitute u back in. So we're going to take this little thing and put it back in there for u. So the natural log of 3x squared plus 1 plus c. Good job. Oh. Sorry, one of the weird computational things, I just figured out what they did, and they just used backwards of the property. I do try to figure out what it is you're doing. So, cool stuff, right? Inverse chain rule, basically, that's what we're doing. It's just more complicated and kind of nosy. You really need a handle on u substitution. In Calc 2, they're supposed to start with this section. So you're supposed to see it twice. There's a good reason why you're supposed to see it twice. This is going to be in, this u substitution needs to be in your toolbox. It needs to be readily available. It's going to be in the little toolbox you carry around, not the big toolbox you keep at home. I'm trying to be figurative. Come on, give me a break. Sometimes you're just no fun. Section 4.5. So when we first, I think it was when I first talked about this chapter, or it may have been in this second section, I'm not really sure. But anyway, we talked about that the area under a velocity curve is the total distance traveled, and that's a kind of cool way to think about these integrals. Oh, wait a minute, I have this typed, I don't even have to write it. The definite integral of the rate of change of a quantity, big F prime of x, gives the total change or net change in that quantity on the interval. So here we're saying, remember how when we defined stuff, remember how we defined it that way? Well, now they're being a little more clear, and they're saying, well, the derivative of big F is, well, that's not the one I wanted, but anyway, we'll go with it, is the output value of big F minus the other output value of big F. And what has that got to do with velocity? Well, that's probably why I should have written that one down, because that's the one we've actually talked about. Come on. So, this is the one we talked about. That, the what?
FV minus FN.
G.
Well, I'm there. Sheesh. So, the area under a velocity curve gives us the total distance traveled. There's a direct correlation there between those two ideas. I've been saying that we do not yet have a way to connect definite integrals and indefinite integrals until we get to the fundamental theorem of calculus. It'd be nice if there wasn't a bar across the middle of that, huh? If a function is continuous on the closed interval, a to b, and big F is an antiderivative of f on the interval closed a to b, then the integral of a to b, the integral from a to b of the derivative function with respect to x is the output variable, the output value of the upper limit minus the output value of the lower limit. Whew, we've kind of talked about that a bit, but now we're saying there is a definite correlation between these ideas. So here we have some vocabulary stuff more than anything else, I guess. For any function on the interval a, b, the difference f of b minus f of b will be called the evaluation of the function on the interval and will be denoted by brackets around big F of x from a to b equals f of b minus f of a. Is that really all that helpful? I don't know, I thought that was, is that anything new? I don't know, but here's more the way we're going to use it. Evaluation notation for the fundamental theorem of calculus says the integral from a to b of the derivative function, it's not really a derivative of the function, but you know, I'm trying to couch this in terms that we understand. The integral from a to b of the derivative function with respect to x equals the integral of that derivative function with respect to x evaluated from a to b. Is that even any more helpful? Well, how about an example? Would that be a little more helpful? Let's do an example because... What?
No, it's good.
Oh, okay. Bye. I forgot to put a dx on my notes. Okay, so what we're going to do here is walk through the process of combining fundamental theorem of calculus into, oh yes, a definite integral and an indefinite integral are related. So let's show that. Here we go. So let's just say that, well, we can use the power function rule, is that what it's called? Power rule? Okay. And so the integral of x to the third power is 1 over 3 plus 1 times x to the 3 plus 1 plus c evaluated from 2 to 4. Well, let's clean that up a little bit and say that's 1/4 x to the 4th plus c evaluated from 2 to 4. And now what we do is we just evaluate it. We plug in 4, that's the upper limit, that's the big F of b, 1/4 times 4 to the 4th plus c minus 1/4, there's the lower limit, times 2 squared plus c. And that equals 64 plus c minus 2 minus c.
Should be 2 to the 4th. It should be 2 to the 4th power.
Oh. happened to my C's? They additive inversed out. I had a plus C and I had a minus C. But typically what we're saying is, but these are just generic holders for C. Except that in this function, they're not generic holders, they're this C and this C. And so you are, this is a value and this is a value, so plus C minus C. The C's just go away and we normally ignore them when we're evaluating definite integrals. Yes, sir?
Shouldn't it be 1/4 times 2 to the 4th, not 1/2?
Yeah, I'm like, my heart is here. That's be 4.
4?
Yeah.
Isn't that the value I had before?
Yeah.
There we go. But anyway, so normally we just ignore the C's when we're doing definite integrals because we're going to add a C, but we're subtracting the exact same C. So they just go away and we can just ignore them. And why would you want to put clutter in there? Right? This just seems like clutter to me at this point. If I don't have this in here, look how much cleaner that looks. Doesn't that look better?
So you're telling us we don't have to put plus C?
Pardon?
So you're telling us we don't have to put plus C?
Not with definite integrals. With indefinite integrals, you have to. But when you have limits that you're plugging in, no, because you're going to add C and then subtract C. So, I mean, you can if you want to, but these get so blessed messy anyway. Yeah, they're just horrible. Yeah, in fact, and I don't even want to do the next one, because it's going to point out an issue that we're going to have. Do I have a black one? Yes, I do. So, to do this out the long way, it took me 3 times to get the right answer. We're going to do it out the long way, just because you need to see the difference between the long way and the short way. So the long way is, well, we only have a few rules here with powers, and so I'm going to separate this out into negative integral from -3 to 3 of x squared, minus 2 times the integral of -3 to 3 of x, plus the integral from -3 to 3 of 3. Whew. And, all right, so now we've got negative 1 over 2 plus 1 x to the 2 plus 1 evaluated from -3 to 3. And we're leaving out the c's. Trust me, you got to leave out the c's here or it's going to go crazy. Minus 2 times 1 over 1 plus 1 times x to the 1 plus 1 evaluated from -3 to 3. Plus 3x evaluated from -3 to 3. And now let's clean that up and see what we've got. -1/3 x cubed evaluated from -3 to 3 minus x squared evaluated from -3 to 3 plus 3x evaluated from -3 to 3. See if I've got it right so far. Looks good.